100 Days Machine Learning Crash Course. Today we want to talk about another classifier called naive Bayes classifier. So far we have learned about SVM, logistic regression classifier, KNN, and another type of classifiers, and today we want to talk about naive Bayes classifier. Okay, let's start with visualization that probably helps to understand the problem better. Okay, let's say we want to classify two types of animals. Let's say the first one is katydids, and also we have the data of grasshoppers. Okay, and we could say that this is abdomen length and this is antenna length. And based on these two features, we want to classify whether an animal is grasshoppers or katydid. Okay, if we have enough data, we could actually plot the histogram and show the distribution of these data. So let's say on the antenna length, we could say that we have something like this probably, and for the grasshoppers we have maybe something like this. Okay, so let's say now we have a new instance, that is a new insect with 3-unit antenna long. Okay, so and actually we want to classify that whether it is katydid or grasshopper. So we could actually can ask ourselves, give the distributions of antenna lengths, what length we have seen, is it more probable that our insect is a grasshopper or a katydid? So we could convert our question into the probabilistic question, okay, as we have seen actually in before. So we could ask actually this question in a more formal way, that is, we want to calculate the probability of class J given the data. Okay, so in here, for example, we know that the new instance has 3 units length antenna. Okay, so let me to actually replot this on this plot to have a better look in here. So we have two Gaussian-like distribution, and let's say now 3 is here. Okay, and let's say this is 2 and this is 10. Okay, so and the red is belong to grasshoppers. Okay, So we could say that we could actually calculate the probability of grasshopper given the data, which is 3-unit long antenna, is equal to 10 over 10 plus 2, which is approximately 83%. And similarly, for the katydid, we could calculate as 2 over 10 plus 2, which is 166, which is approximately 16%. Okay, so we could say that from this plot, the new instance is more likely to be a grasshopper, okay, in comparison with katydid probability. And so the examples that I shown you, it is a simple example of naive Bayes classifier, okay, that we want to talk more about it. Hope that you got the general idea of that classifier. Okay, so for unseen instances, we want to simply pick the most probable class. In other words, we want to calculate, we want to pick the class with the most probable probability, okay? And for calculating this, we could use the Bayes theorem, which is P of D given Cj, which is class of J times P of Cj over P of D. Okay, and we know that this means that the probability of instance D being in class Cj, this is the P of D is probability of instance D occurrence, and P of D given Cj means that the probability of generating instances of D given class Cj, and P of Cj is actually probability of occurrence of class Cj. Okay, so let's see. So in here, actually this is, in here we want to build a Bayes classifier. We will say that how we could convert that into naive Bayes classifier, but and what does it mean to have a naive Bayes classifier. But now this is actually Bayesian classifier. Okay, so let's see another example. Let's say we have an officer. His or her name is Drew, and we want to know that whether the officer is a male or female. Okay, and we have a small database for this. So this is name, this is sex, then we have Drew officer, which is male. We have Claudia, she is female. We have Drew, female. Again, another Drew, female. We have Alberto, he is male, and Karen is female. Nina is female, and we have Sergio, which is male. Okay, now the question is we want to actually ask is that we want to now calculate this probability using the Bayesian theorem. Okay, in fact, now we want to calculate the probability of the officer being male given his or her name, which is true. Okay, if we use this Bayesian theorem, we could write it as probability of true given male times P of male over P of true. Okay, now let's calculate this from the table. The probability of true given male, so we know that we have in this one and this one, which is corresponding to the male, and for true we have one, just one, right? So it is 1 over 3 times the probability of male is 1, 2, 3 out of 1, 2, 3, 4, 5, 6, 7, 8, right? So it is 3 over 8, and the probability of true is 1, 2, 3 over all of 1, 2 to 8, right? So it is 1 over third. Now now we know the probability of male given true, which is given the data. Okay, now we should calculate the other class probability, which is the probability of female given true. Okay, again we could write that as probability of true given female times probability of female over the probability of true, right? So the probability of true given female, so we should look just at these, this one, this one, this one, and this one. Let me to show that with another color to just confusing. Okay, this one, this one, this one, and this one. So we have 1 true, 2 true in here, so it is 2 over 1 through 1, 2, 3, 4, 5. So we have 2 over 5. The P of female is actually 1, 2, 3, 4, 5, which is actually this one, over 8 over P of true, which we calculated that, which is 3 over 8. Okay, so it is actually is 2 over 3, right? So you could see that now the P of female given true is greater than P of male given true. So the Bayesian classifier tells us that the new data, which we know his or her name, which is true, is most probable to be, which is more likely to be female than male. So our prediction is female. Okay, so this is Bayesian classifier. Just note that in this example, we actually didn't have to use Bayesian theorem to calculate the probabilities. So for example, for calculating the P of male given true, we could actually calculate this without the Bayesian theorem. So you could, for this one, we could consider just true. Then for calculating the male, this is 1/3. Okay, so you could just actually have the result directly, but note that when we have more complicated situations or real valued problems or more features, we need to use Bayesian theorem to calculate the probabilities. Okay. Now let's say we have more attributes or more features than just one. So now we have name. We have another attribute which is over 170 centimeters. Eye color, hair length, and sex, which is the label. Maybe it is better to show that we have another color because it is the label. Okay, so first one is Drew. Let's say no, blue, short, male. Claudia, yes, brown, long, female. Next one is Drew, no, blue, long, female. Drew, no, again blue, long, female. Alberto, yes, blue, long, male. And we have Karen, no, blue, long. So this is short actually. Long, female. And we have Nina, yes, brown, short, female. And we have Sergio, yes, blue, long, male. Okay. So now we have more features than just one attribute. In the previous example, we just had one feature and one label. Now we have 1, 2, 3, and 4 features or attributes for the label. Okay, so this is in here naive Bayes decision comes to the game. So in naive Bayes classifier, we assume attributes have independent distribution. So the most important thing about naive Bayes classifier in comparison with Bayesian classifier is that in naive Bayes classifier, it assumes that the data distribution, the attribute distributions are independent distributions for attributes. Okay, so we could write the P of data given Cj as, because for data now we have 4 attributes, for example, in here, or in general if we have n different attributes, we could write the data as the first attribute, the second attribute to the n attribute given Cj. Because of the independence assumption, we could actually factorize this term to the multiplication of d1 given Cj P of D2 given Cj to P of Dn given Cj, right? So this is the assumption of naive Bayes classifier. Okay, so in this example, so we could write the P of, so let's say now our test data has some properties. The name of officer is Drew. We know that he or she has blue eye colors, and he or she is over 170 centimeters, and he or she has long hair. Okay, now we want to know is the officer is male or female. So now we could calculate the P of Drew given female as using this factorization in here. We could say that it is equal to P of, so this is not just Drew, so this is Drew and blue eye color over 170 and long hair. So we could write that as P of Drew given female times P of blue eye color given female, P of over 170 given female times P of long hair given female. So we could now calculate this as 2 over 5 times 3 over 5 and so on. Okay, now we could calculate all of these probabilities, and also for so just note that we should calculate the P of female given the data. So when you use the Bayesian theorem, then you should calculate this one times the P of female. Okay, and you should do the same for P of male, right, to get to actually make the decision that whether the new data is male or female. And actually we could show the naive Bayes classifier with the graph that actually we talked about graph for some sessions. So hopefully now you know how to show the naive Bayes classifier as the graph So in here we have conditional probability distributions, and in here this is the P of Cj. So let's sum up the Bayesian classifiers and their properties, advantages and disadvantages. The advantages of Bayesian classifier is that it is fast actually to train and actually fast to classify for new instance. So if you remember that, for example, in KNN, it was fast to train but not fast for classification, because we should calculate all of the distances to our test distance, to our test data, then make the decision. So it could be time consuming for KNN, but in Bayesian classifier it is really fast, and it is not sensitive to irrelevant features. Because if you have irrelevant features, then for calculating both of your classes, that those features probability have the same effect in both the classes. So it is not sensitive to irrelevant features, and this is actually good. It could handle real and discrete value. And this is also a very good thing. It could both handle real and discrete data, and also it handles streaming data. But the disadvantage is that it assumes that we have independent data features, which is actually in many of the times and tasks, and this is not a very true assumption. For example, let's say we have an image. So in image, if I tell you we have something like this, and let's say I just okay, so let's say this is a face, this is a good face, then, but as you could see, let's say the pixel values are features, and some pixel values, as you could see here, are missing. For example, in here we have a discontinuity, and also in here, but you could guess that actually you could connect them. So it means that the data pixels are not uncorrelated. They are actually correlated and have some spatial correlation with each other. So for example, in this case, you could not use the naive Bayes classifier. Maybe you are able to somehow convert or extract some features from this image and try to build some independent features, for example, with using PCA or other methods to build independent features. Then using naive Bayes classifier could be a good idea. Another solution is that actually not using naive Bayes classifier and try to use other graphs than naive Bayes to consider the relation and connections between the features. For example, if we add these kind of connections that we actually studied them in the graph and Bayesian networks, so in those cases we could actually make valid assumptions about data and features connection. But they maybe make the classifier more complicated and more and harder to train. So, but now you know a very simple and actually good classifier to maybe start with in when you know that your features are independent. Okay, now let's see an example in scalar. Okay, now let's see the example. I opened a Jupyter notebook and import some packages, and now I load the iris dataset, and converted it to pandas data frame. Okay, for this example, we want to use a sub data frame of diverse data set, let's say sepal length and sepal widths. Let's put this in here. Okay, now if we, and actually we need the target, so if we print add, okay, now we want to work on this. Let's name it data frame, is more convenient for us. Okay, the first thing that maybe it is good to see the distribution. So for this I import seaborn. We could use the joint plot, and so you should have an X and Y, so we use the pair plot to have, so in here we have the data frame. Okay, so actually this is the distribution of sepal length, and this is the histogram or distribution of sepal widths in here. Now I think we could pass a hue, which in here is target. I think because we could actually plot that with another way. So instead of converting that to a categorical thing, we could actually use the dist plot of sepal length. So we need CF sepal length, and in fact we want to plot first target is 0. Okay. Yeah. Okay. And also for another target, we could actually plot that distribution. And also other distributions, as you could see in here. So they are like normal distributions, as you could see in here, for sepal length, and also for sepal widths we have a similar thing. Now let's say we want to apply a naive Bayes classifier. So for this you could just search how to use naive Bayes classifier in Scalar. So in here there is a Gaussian naive Bayes classifier, so you could import that and just, yeah, and you could call that CLF, which is classifier. Then you should fit that on your data, which is now we have df. So if we remember, we have drop, and we have the classifier for y, which is target values, right? So now we have Bayesian classifier. Okay, so in that case, you could actually easily use naive Bayes classifier. Maybe it is good to see the performance of classifier. So we need train test to split. It is in scalar model selection. So let's say in here, from scalar dot model selection, import train test to split. Okay, now we have train x of train for df train df test is equal to train test split of df and test, I think it is test size or something. Yeah, it is test size. Let's say we want to put aside 20% of data, so we could see the head of the training data and test data. Now we split our data to training and the test data. So in here we should fit the classifier on the training data, and guess what? So in here also for y you should use the df train. Okay, now we want to get the score of classifier, so we could use accuracy in a scalar to evaluate your classifier performance. Okay, so if we import it, then we have to pass the true or grand truth target, which in this case it is test target. They are real targets. And for y of prediction, which is the classifier prediction, we could use clf dot predict of the test data, which is df test dot drop. So we should drop the target from the data set. Okay, so as you could see, it is 73% accuracy for our classifier. Maybe it is not bad to actually make a comparison with ANN in here, to just for the sake of comparison. So from scalar.neighbors import k-near neighbors classifier, and okay, now so we have another classifier. Let's call it clf2, which is k-nearest neighbor. So we just use the default values in here, and after that we want to fit it again like this. So we just copy and paste it in here. Okay, now also we want to have this for, let's call it y2 clf2, and we want to print this one and also print this one. Okay, so if you run that, wow, we could see that both classifiers have the same accuracy on the test data. Let's change this is neighbors or neighbors. Let's change it to see the effect for 10. Okay, so wow, I got it. So mistake is that in here we should have y-2. Sorry about that. So now we could see the KNN classifier performed better in here in comparison with naive Bayes classifier. So actually we should be aware that sometimes a classifier performs better, not a classifier performs better in all the situations. So depends on the situation. We should actually try different classifiers and pick the best one. Okay, now I think that's it for this session. We learned how to use Bayesian naive Bayes classifier and what is naive Bayes classifier. Okay, see you in the next session. Bye.